This is the Roland High School IB Physics Summer Podcast number 4, The Blackbody Law. Okay, welcome back. And as we begin podcast number 4, we are starting chapter 7.2, which is the greenhouse effect and global warming. And the first topic that we are going to tackle is that of blackbody radiation. So let me ask you, have you ever seen an object glow red hot? Of course you have. Maybe it was a bed of coals in a fireplace, maybe a campfire, maybe the red hot charcoal sitting at the bottom of your barbecue. Here's a picture of the exhaust manifold of an automotive engine, and you can see that the headers here are glowing red hot. High temperature, they give off electromagnetic radiation, this case in the visible range, and we can see them glowing. When things get very hot, they glow. But why? Well, it turns out that when a charged particle is accelerated, it radiates electromagnetic waves. This is how radio transmitters work, for example. Electrons are caused to run up and down an antenna, and they give off electromagnetic waves in the form of radio waves. Well, atoms are vibrating, and atoms have charged particles in them. So when an atom is vibrated, an atom radiates electromagnetic waves. So as a result of that, any object that has vibrating atoms, which is any object that has any temperature at all, it turns out gives off electromagnetic waves. So here's an example. In a light bulb filament, moving charges do work. They cause the atoms to jiggle in the filament. Think back to our analogy of the people running through a group of people dancing, jiggling them and jostling them. So as electrons move through a very thin wire, say a tungsten filament in a light bulb, that causes the atoms in the tungsten to vibrate those faster. Those jiggling atoms are accelerating as they wiggle back and forth. The vibrating charges cause electromagnetic waves to be radiated. In the case of a light bulb, some of the electromagnetic waves that are radiated are in the visible light spectrum, so we can see them, thus light bulb. You've probably seen infrared cameras. Search and rescue teams can use these cameras to spot objects that are warmer than the background surroundings. So, for example, a lost hiker, will show up brighter on a camera, in an infrared camera, than the background will. Why is this? Again, all objects that have a temperature, they don't have to be super hot like a light bulb filament is. All objects that have a temperature have moving atoms, and therefore all objects give off electromagnetic radiation. So right now, as you're sitting here listening to this podcast, because your skin has a temperature, probably somewhere around 37 Celsius, you convert that to Kelvin, you are giving off electromagnetic radiation. Well, you're not giving off visible light, you're not glowing in visible light, but you're giving off longer wavelength radiation in the form of heat that we call infrared radiation. So what determines the wavelength of the electromagnetic waves? Well, it turns out it's the temperature. The hotter an object is, the shorter the wavelengths that tend to be given off by this radiated energy. What determines the power, the amount of energy that's being given off? Again, it's the temperature. Hotter objects radiate more joules of electromagnetic energy per second, more power, in other words, than cooler objects do. So again, the relationship between temperature and the wavelength given off is that hotter objects tend to give off shorter wavelengths of electromagnetic energy. Again, what's the relationship between temperature and power? Hotter objects, as you might expect, radiate more power. Now, it turns out that when an object is radiating electromagnetic radiation because it's got a temperature, it doesn't radiate at just one frequency or just one wavelength. It radiates at a broad spectrum of wavelengths. But there is a maximum, a peak, and we're going to look at some graphs in just a minute that'll kind of illustrate this. Okay, the first graph here is of a relatively hot object. The temperature, as you can see, is 1250 kelvins. Notice that there's a broad, first of all, the x-axis is wavelength. Okay, the left-hand side is short wavelength, starting from 0. Toward the right-hand side of the x-axis is longer wavelength. For meaning lower frequency. If you look at the y-axis, that's the power being emitted by the object. Higher meaning more power. So notice there's a broad range of wavelengths being emitted by this object, but there's a peak. I want you to look and notice, remember where that peak is. Also try to notice and remember how high, how tall that peak is. Okay? All right, here's a graph of a hotter object. What's happened to the amount of power? What's happened to the peak, the height of the peak compared to the first graph? Okay, you should notice that it's taller, it's higher. So the hotter object is radiating more power. The temperature of this hotter object is 1500 kelvins instead of 1250. Okay, what's happened to the peak wavelength? Now again, notice that we're radiating energy at a broad range of wavelengths from very short to very long. But look at the peak, compare it to the original peak. Okay, you should notice that it's shifted to the left. The peak wavelength when the temperature was hotter, when the temperature is higher, the peak wavelength is a lower, shorter wavelength. Okay, take a look at the next graph. Here's an object that's even hotter, at 1750 kelvins. And notice that the peak is considerably higher. The power is going up pretty rapidly here as we increase the temperature. And again, this is a little more subtle, but notice that the peak wavelength being emitted is shifted once more towards shorter wavelengths. So higher temperature means more power. Higher temperature means a shorter maximum wavelength, a shorter peak, I should say, wavelength. Okay, let's look at the next graph. Here we have an object that's at 2000 kelvins, quite hot. Notice that the peak power is very high. Okay, so lots of power being radiated by this hotter object. And notice again, this is a little more subtle, but notice that the peak wavelength, the top of the graph, is a shorter wavelength than the lower temperatures were. So again, to recap, when an object has temperature, as all objects do, they radiate electromagnetic energy. They radiate a spectrum of real short to long wavelengths. But the peak, the maximum, the wavelength that's emitted the most, gets shorter as the temperature of the object gets higher. Also, the amount of power being emitted gets greater as the temperature of the object gets higher. Since physics is a quantitative science, you might suspect that there's a quantitative way to express the relationship between temperature and peak wavelength, and temperature and the amount of power radiated. And in fact, there is, and it's called the Stefan-Boltzmann Law. So if you take a look at the first equation here, this is this equation is showing the power that's being emitted. This is the power, the joules per second of electromagnetic radiation being given off by an object. Sigma is a constant. It's called the Stefan-Boltzmann Constant. It's in the front of your data booklet. You can look it up. The capital A is the area. Objects with bigger area radiate more energy. That might make sense to you. If you took a mouse at the same temperature approximately as a human, the area of the mouse's skin is much smaller than the area of a human's skin. So a human gives off more joules of energy per second than a mouse does. But interestingly, if the mouse and the human are at about the same body temperature, then the wavelength, the peak wavelength given off by both the mouse and the human will be the same. They're both going to be in the infrared range. But again, the human, as you might expect, gives off a lot more energy per second because of that area parameter. Something else in this equation that's pretty interesting to me is if you look at the temperature, its power goes as the fourth power of the temperature. There are very few equations in physics, I can't think of any other off the top of my head, that have a fourth power in them. So what that means is as the temperature increases by a pretty small amount, the power radiated increases by a pretty large amount. Again, if you think of those four graphs we just looked at, by changing the temperature by a relatively small amount, the power increase very, very rapidly. Okay, let's look at this next version of the Stefan-Boltzmann law, the next version of this equation. and you notice it's got a little E in front of it. Okay, so what's the E all about? Well, the first version of the equation that didn't have the E is for what's called a perfect emitter, an object that emits energy as perfectly as possible. Okay, and that's called a black body. Real objects don't necessarily emit as well as a black body does. So this E value is called the emissivity parameter, and it's a number between 0 and 1. So if E equals 1, then that multiplies the equation by 1. That's a perfect emitter. Okay, that's as good as it gets. If E has a value of 0, that means no matter how hot the object is, it's not going to radiate any energy. So there's a graph in your, or actually a chart in your book on page 435 that shows that different objects have different emissivities. The emissivity of ocean water is 0.8, for ice it's 0.1, for dry land it's 0.7, for land with vegetation it's 0.6. And again, for a black body, which is a theoretical object, the emissivity is 1. So that E value is just kind of a fudge factor that goes in front of the equation to tell you how well the object emits. We said that the peak wavelength that's being emitted by a black body depends upon the temperature. So here's an equation that shows you the relationship between the temperature in kelvins of the object and the peak wavelength, the wavelength that's emitted most strongly. Remember that all objects that have temperature radiate a range of wavelengths from short wavelengths to long wavelengths. But the wavelength that's emitted most strongly, the peak wavelength, is calculated by this equation. So as you can see, as the temperature gets higher, as T gets larger, lambda is going to be smaller. So hotter objects tend to radiate shorter wavelengths. This equation can help you understand why we need an infrared camera if we want to pick up an image of a lost hiker, but we can see a light bulb with our own eyes. The temperature of the human body is low enough that the primary emissions are in the infrared range, so our eyes don't see infrared. We need a special camera that can detect the infrared radiation. On the other hand, a light bulb is a whole lot hotter than the surface of your skin, and the peak, because T is higher than lambda, is shorter. The peak wavelength is up closer to the visible light spectrum. There's enough energy being emitted by a light bulb in the visible light range that we see it glow. The surface of the sun is very hot, 5,800 kelvins. Its primary emission is in the visible light range again. That's why we can see it. We don't need a special camera to detect it. So to wrap this podcast up, let's just recap a little bit. Objects that have temperature, which means everything, give off electromagnetic radiation. The amount of radiation, the joules per second, the power, depends upon the temperature. In fact, it varies as the fourth power of the temperature. Hotter objects radiate more joules per second of electromagnetic energy. I don't think that's going to be too hard to remember. A little more subtle effect, not as obvious at least, or intuitive, is that the hotter an object is, the shorter the wavelength of the maximum amount that's being radiated, the shorter the peak wavelength will be. And here's an equation for calculating the peak wavelength, and there's an equation for calculating the amount of power. And that pretty much sums up Blackbody radiation, which is called the Stefan-Boltzmann Law, which is the first part of Chapter 7.2. If you have any questions about this material, please send me an email or post a message on the CAS Manager, our group. Okay, thanks a lot. See you next time.